Tonight, we're going to explore one of the most quietly humbling engineering questions in modern spaceflight. The question is whether a permanent crewed base on the moon, a place where humans live and work continuously, is something our civilization can actually build, or only something we can imagine building. The moon sits about 384,000 kilometers away, close enough to see with the naked eye, close enough that 12 people have already walked on its surface. And yet, the greatest obstacle to living there may have nothing to do with distance. Hidden beneath every proposal, every habitat design, every ambitious roadmap is a problem so fundamental that it quietly turns a nearby destination into something far more difficult than most people realize. To land a single useful ton of equipment there, we have to launch a stack that weighs roughly 50 times as much. 85% of that liftoff mass is propellant. Only 2 or 3% of the original rocket ever reaches the lunar surface as something a crew can use. Every shield against radiation, every liter of water, every spare part, every backup must be lifted out of one gravity well and lowered into another. Each new hazard adds mass. Each added mass demands more fuel, and the fuel itself must be lifted too. By the end of tonight, you're going to understand why the rocket equation quietly governs everything, how compounding hazards like radiation, vacuum, dust, and low gravity turn an engineering project into a civilizational one, and why the honest answer to a permanent moon base is not never, but not yet. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. The rocket equation is the reason, not the vacuum, not the dust, not the radiation. Those come later. The first obstacle is the math. And the math is not linear. That is the part most people miss. On Earth, if you need to move more material, you send more trucks. The relationship is roughly 1-to-1. Double the load, double the fleet. It scales in a way that feels manageable, like a construction budget. Space does not work that way. Space is a war with exponents. There is a relationship at the heart of rocketry that ties three things together: the speed you need to reach, the mass of the rocket when it is full of fuel, and the mass when that fuel is gone. You do not need the formula. You only need the shape. As the required speed goes up, the ratio of full mass to empty mass does not go up by the same amount. It goes up steeply, disproportionately. Each additional kilometer per second you need costs you more than the one before. Think about what that means in practice. Reaching low Earth orbit, the first step into space, requires a velocity change of roughly 9.4 kilometers per second. That is about 21,000 miles per hour. To get from orbit to the lunar surface and back into orbit takes roughly another 6 kilometers per second, depending on the exact profile. Every part of that velocity is paid for in fuel. For a typical large chemical rocket, roughly 85 to 90% of the liftoff mass is propellant. Out of 100 tons sitting on the launch pad, maybe 10 to 15 tons is structure, engines, and payload combined. Payload is only a fraction of that. Stack the stages needed to cross from Earth orbit to the moon, and the fraction of the original launch mass that arrives as useful gear on the surface drops further. The working number is around 2 to 3%. Not a modest loss, not a rounding error, 2 to 3%. Here is what that number means concretely. Imagine a pressurized module on the lunar surface, roughly 50 tons. That is about the mass of a large road truck, a single room with equipment inside. At 2%, that one room implies a starting stack on the launch pad of around 2,500 tons, 2.5 million kilograms, mostly built, mostly launched, and mostly burned, to leave one pressurized chamber sitting in the dust. A fuel iceberg. The module is the tiny tip above the surface. Everything underneath it, the propellant, the tanks, the stages, burned and scattered across the flight path. And that 50-ton module is not a base. It is one room. A real base needs far more than one room. Radiation shielding, rovers, a power system that can run through 2 weeks of lunar night. Food, water, air, water treatment, waste processors, medical gear, communications, computers, tools, pumps, valves, and circuit boards. And because things break with no parts store nearby, 2 or 3 backups plus spares for every critical system. A small rover weighs hundreds of kilograms. A serious power system weighs many tons. 10 extra tons of equipment on the moon can mean hundreds of extra tons of propellant and hardware launched from Earth. Here is where it gets strange. The structure that holds all of that equipment has to hold more equipment than you originally planned. Stronger floors, heavier walls, more bracing. Stronger structure weighs more. More mass means more fuel. More fuel means larger tanks and larger rockets to push those tanks. The loop closes on itself, and it does not close gently. Now consider what the distance actually means. The moon is roughly 384,000 kilometers away, about 239,000 miles. Against the distances to Mars or beyond, that sounds close. It is close in kilometers. But a rocket does not measure distance in kilometers. It measures distance in energy. Getting to the moon means escaping a deep gravity well, completing an interplanetary transfer, and executing a powered descent against lunar gravity. Kilometers are almost irrelevant. Energy is everything, even at an optimistic $1,000 per kilogram to low Earth orbit. That is only the first step. Getting from orbit to the surface needs additional stages, most of whose mass is again fuel. The effective cost per kilogram actually landed on the moon can reach many tens of thousands of dollars. 1 kilogram is roughly a liter of water. A single liter of water delivered to the surface can cost more than most people earn in a month. A 100 kilogram electronics rack, or a 90 kilogram person, carries a price tag in the millions. The imagined base is not walls and air. It is, first, columns of money turned into fuel. This is the first filter. Not the engineering challenge of building a habitat. Not the medical challenge of protecting the crew. The first question is whether a civilization can afford to lift and land all the hardware, all the spares, all the backup stages, at a cadence fast enough to keep the base alive. Stacking the rocket equation with the compounding mass of everything a human outpost requires pushes the answer from hard to something closer to borderline impossible for a normal economy. But the rocket equation is only the beginning of the problem. Because once you land, the environment waiting on the surface has its own plans for anything you manage to bring. Suppose, somehow, we can pay for the launches. Suppose the rocket equation gets solved well enough, and the hardware lands. A crew steps out onto the lunar surface. What greets them first is not dust or darkness or silence, though all of those are waiting. What greets them first is invisible. It is the sky itself. On Earth, you are surrounded by 2 shields you never think about. The first is the atmosphere, roughly 1 bar of air overhead, a column of gas that absorbs and scatters enormous amounts of solar and cosmic radiation before it reaches you. The second is Earth's global magnetic field, which deflects charged particles streaming in from the sun and deep space, bending them away the way a river parts around a stone. Together, they reduce the worst incoming radiation to livable levels, and you walk through it every day without noticing. The moon has neither. The lunar surface sits under a near-perfect vacuum. There is no thick blanket of air. There is no strong global magnetic field. High-energy particles from the sun, and from sources far beyond the solar system, strike the surface nearly unimpeded. This is the baseline condition. Not a special event, not a storm. The everyday environment. Measurements from lunar orbit and the surface put the daily radiation dose at roughly a few hundred microsieverts per day under typical conditions. A person on Earth receives a few microsieverts per day from natural background, a few millisieverts over a year. The lunar rate runs several times higher, persistently, every day, as the new normal. A year on the unshielded surface would consume a large fraction of a professional radiation worker's permitted yearly allowance, and that assumes no storms hit. Storms hit. The sun periodically erupts in solar particle events. During large flares and coronal mass ejections, enormous numbers of high-energy protons are thrown outward. Near Earth, the magnetic field and atmosphere absorb most of it. On the moon, the particles arrive directly. A strong event can deliver more than 1 sievert through thin shielding in a matter of hours. 1 sievert is 1,000 millisieverts. At that level, long-term cancer risk rises clearly. A few sieverts received quickly crosses into acute radiation sickness, nausea, vomiting, damage to blood cells and bone marrow. At high enough doses, without immediate treatment, it can be fatal. The clean white dome is not a viable design. Here is where the engineering forces itself into view. To protect against both the steady baseline and the storm spikes, the habitat needs serious shielding. Not a thin aluminum shell, not insulation, meters of material. Lunar regolith piled thickly overhead, or dense regolith brick walls, or tanks of water arranged around the living spaces. Water is actually an effective radiation shield, because hydrogen atoms in water absorb and scatter high-energy particles well. But water is heavy. Everything is heavy. And heavy things must arrive through the rocket bottleneck described in the first problem. Some planners suggest simply shipping shielding from Earth. Let's think about what that actually means. To cut high-energy galactic cosmic rays to acceptable levels, you need a substantial amount of mass per square meter of roof and wall. The estimates run roughly 5 to 10 tons per square meter. Take a modest habitat with about 100 square meters of exposed surface. That is roughly the footprint of a modest house. At 5 tons per square meter, that habitat needs 500 tons of shielding. At 10 tons per square meter, it needs 1,000 tons. That number is just the shielding. Before structure, before life support, before power systems, before the crew, 500 to 1,000 tons of shielding alone for one small habitat. Through the launch math from the first problem, that figure becomes something that no current economy can absorb without extraordinary national commitment. Importing the shielding from Earth is not a backup plan. It is not a fallback. It is, as a solution, essentially impossible for routine operations. So the answer is to use what is already on the moon. Regolith is free. The surface is covered in it, meters deep, fine-grained and loose from billions of years of micrometeorite impact. The right instinct is to dig it up, pile it on top, use it as a natural radiation blanket. This is the right instinct. But it does not solve the problem. It relocates the problem. Moving regolith requires excavators, loaders, bulldozers, machines that dig trenches and fill heavy bags, or 3D printers that bond regolith into bricks. All of it must survive the lunar environment for years. Temperature swings of more than 250 degrees between lunar day and night, from above 100 degrees Celsius in sunlight to around minus 170 in shadow. Sharp, abrasive dust working into every seal and bearing. Vacuum that changes how lubricants behave. And every excavator, every spare motor, every hydraulic seal is mass that had to be lifted from Earth, inserted into lunar transfer orbit, and landed softly. The rocket equation does not go away because you decided to use local material. It re-enters through a side door, and then there is the part that the numbers cannot settle, because the data does not exist. We have never tested human biology under the specific combination of deep space radiation and low gravity over years. All long-duration spaceflight so far has happened on the ISS, in low Earth orbit, still inside Earth's protective magnetic field, and in microgravity rather than 1/6 gravity. A moon-based crew would face a different radiation environment and a different gravity environment at once, for years, with no historical data on what that combination does to cardiovascular health, bone marrow, the nervous system, or long-term cancer risk. A moon base would be that dataset. The people living in it would be generating the evidence while depending on their own health to keep the base running. They are the test subjects and the repair crew at the same time. If the results come back worse than predicted, there is no clean undo. Returning a full resident population to Earth is enormously expensive. Some of those residents, after years at 1/6 gravity, may not tolerate full Earth gravity at all. The biology could be irreversible in ways that are simply not known yet. Maybe careful shielding and preventive medicine keep the risk at manageable levels. Maybe the combination of radiation and low gravity interacts in ways current models underestimate, producing higher cancer rates accelerated cardiovascular disease, damage to the nervous system. Both outcomes are genuinely possible. Neither is ruled out. Radiation alone turns the moon from a place you visit briefly into one that constantly draws down a health budget that cannot be easily replenished, wrapped in infrastructure heavy enough to make the rocket equation wince all over again. The shielding problem and the biology problem together are just the second challenge. The surface itself still has more weighting. Now, set biology aside for a moment. The body's slow accumulation of invisible damage is one kind of threat. The surface itself presents another kind entirely, and this one is visible, measurable, and extreme in ways that most Earth engineering has never been asked to handle. Watch the moon's day turn into its night. Not a familiar 24-hour cycle with a brief cool night and a warm afternoon. The moon completes one full rotation relative to the sun in about 29.5 Earth days. That means roughly 14 days of unbroken sunlight. Then roughly 14 days of complete darkness. The cycle just keeps turning, month after month, year after year. In that direct sunlight, the surface climbs to around positive 120 degrees Celsius, roughly 250 degrees Fahrenheit. When the sun drops below the horizon and the long night begins, the surface plunges to around negative 170 degrees Celsius, around negative 274 degrees Fahrenheit. The total swing between those two extremes is close to 300 degrees Celsius. Not across seasons, the way Earth cycles through summer and winter. Across a single month, over and over again. Metals expand when heated and contract when cooled. Seals harden in cold and soften in heat. Solder joints flex at every cycle. Cables, hinges, connectors, and pipe joints are pulled one direction for 2 weeks, then the opposite for 2 weeks. On Earth, most machines see swings of a few tens of degrees a day. Lunar hardware is dragged across nearly 300 degrees, repeatedly. Small stresses accumulate. Tiny cracks grow. Seals lose their grip. The structure is not just surviving the temperature, it is running a slow-motion fatigue test, continuously, for years. Inside, the crew needs something close to normal room temperature, roughly 20 to 25 degrees Celsius, around 68 to 77 degrees Fahrenheit. The habitat walls must hold that stable interior against whichever extreme the surface is currently delivering. During the long day, the outside bakes. During the long night, it freezes. Thermal control cannot stop. It cannot fall behind. Falling behind during the day means the interior overheats. Failing during the night means the pipes freeze and the air turns cold enough to be dangerous. And all of this happens while the surrounding structure is contracting and expanding with the same cycle. Solar power looks like the obvious answer on the moon. No clouds, no weather, no atmosphere scattering the light. The panels sit under clean, hard sunlight and convert it efficiently. For about 14 days, solar power works well. Then the sun sets and output drops to essentially nothing. To keep life support running through more than 350 hours of lunar night, the base needs stored energy. Life support alone demands continuous power for air circulation, carbon dioxide removal, oxygen production, water circulation, and heating. Add computing, lighting, communication, and the base is drawing somewhere between tens and hundreds of kilowatts at all times. Multiply that continuous draw by roughly 14 days, and you arrive at megawatt hours of stored energy. Now add the heat rejection problem. Even once power is solved, all of that power eventually becomes waste heat inside the habitat. On Earth, you dump waste heat into the air around you. The atmosphere carries it away. On the moon, there is almost no air. Convection. The process of heat moving through circulating fluid or gas essentially does not work. Heat can only leave through direct solid contact with something else, or through radiation. Radiation means infrared light, energy glowing invisibly outward into space. So the base needs radiators. Large panels oriented to face cold space, glowing in infrared, slowly bleeding heat away. This is the only viable cooling mechanism available. But the same regolith that shields the habitat from radiation turns the cooling problem into a conflict. The buried bunker that solves radiation also wraps the habitat in one of the best thermal insulators on the moon. Regolith does not conduct heat well. which helps slow the brutal swings from outside, but becomes a serious obstacle when you need to move heat from inside the habitat out to a cooler radiator. You end up with a habitat wrapped in a thermal blanket, trying to pump heat through that blanket to radiating panels that must face clear space without being shadowed by your own structure. The thermal control system doing all this is not one device. It is pumps, pipes, valves, heat exchangers, and radiators working together across a range from warm interior to deep exterior cold. A pump stalled by partly frozen lubricant can take down the whole cooling loop. A cracked pipe can dump coolant and end temperature control without warning. During the long day, it fights heat coming in from the baking exterior, while dumping heat generated inside. During the long night, it prevents freezing while still moving waste heat out to space. It has to do both, without failing, for years. And outside the controlled bubble, the exposure is worse. Any equipment left idle during the long night, a parked rover, a robotic arm, a crane between tasks, can cold soak below minus 50 degrees Celsius for the full 2 weeks. Many lubricants freeze solid or turn glue-like. Different metals contract by different amounts, pulling at joints from multiple directions. Imagine a car parked in a deep freezer for 2 weeks, then expected to start and drive at full performance, repeated hundreds of times over several years. The bearings wear faster, the coatings crack, the cables stiffen and eventually break. Most space hardware currently in use is not tested for hundreds of such extreme cycles while doing heavy industrial work at the same time. Designing machinery to survive this for decades pushes materials and engineering well beyond anything Earth industry normally demands. And every failure in this environment means a spare part that was launched at enormous cost, and a person in a pressure suit working in the same thermal extremes to make the repair. The biology problem and the radiation problem together were the second challenge. Temperature is the third. And the list does not stop here. Stay outside for a moment longer. Look at what surrounds the equipment, the walls, the joints, the sealed doors. Not cold air, not thin atmosphere, not even a trace of pressure. Nothing. An absolute vacuum that extends in every direction without interruption. And that nothing is the fourth challenge. Inside a lunar habitat, the air needs to sit at roughly 50 to 100 kilopascals of pressure, about half to full sea level pressure on Earth, somewhere between 7 and 15 pounds per square inch. Outside, the pressure is so close to zero it might as well not exist at all. That gap does not close. It does not relax at night or during quieter operational periods. It is there every second the base is occupied, pushing outward through every surface the habitat has. Think about that constant load on the structure. Every square meter of wall, ceiling, floor, window, airlock, hatch, and joint is part of a single pressurized vessel trying to inflate outward, like a balloon held in a rigid shell. On Earth, a cracked wall sags and leaks water, and you call someone. On the Moon, a through crack vents breathable air directly to vacuum. The habitat begins to depressurize, and the crew has minutes at best to reach a sealed volume, close hatches, and stop the loss. Not hours, minutes. That single consequence reshapes every decision about how the structure is built and maintained. Every weld must be solid. Every bolt must stay tight across decades of thermal cycling. Every gasket must keep its flexibility without developing microfractures or losing its seal. There is no threshold of good enough. The structure must behave like a spacecraft or a submarine, a vessel that cannot afford gradual failure. Except, it is not a spacecraft that flies for a week and returns. It is a place people live in for years, enter and exit constantly, modify, expand and repair while the pressure load never lets up. But the reality was different. The most dangerous failure mode is not the dramatic one. Rapid decompression from a significant breach is terrifying, and planning for it matters, but the quieter enemy is harder to find and harder to stop. Air molecules are tiny and they move constantly. Any path through the shell, however small, leaks gas, a microscopic pinhole, an imperfect seal line along a hatch frame, a hairline scratch in a gasket seat that lets molecules slip past in single file. These leaks are invisible, They make no sound, and they are relentless. A few grams of air per second sounds almost negligible, but a habitat holds several tons of breathable air. A steady, undetected leak at that rate can bleed the reserves down over hours to days without triggering obvious alarms. This is why the base needs pressure sensors in every section, cross-comparing readings continuously, flagging drops that might be real loss against drops that might be instrument error. It needs automatic isolation valves between modules, so a compromised section can be sealed off without flooding the whole habitat with emergency conditions. And redundancy cuts both ways. A false alarm that shuts down half the base at the wrong moment is also dangerous. Then, there are the people who have to find a leak that may be anywhere on a shell of hundreds of square meters and fix it from the inside. And leaks do not always appear immediately. A defect may sit dormant through the first 50 thermal cycles and open on the 100th. A nearby micrometeoroid impact can flex the wall just enough to open a seal that was borderline for months. Some defects only appear under full operating pressure, invisible at lower loads. On Earth, you would spray soapy water on a suspect joint and watch for bubbles. In lunar vacuum, on the exterior of the habitat, that option does not exist. You are hunting gas escaping through bonds you cannot directly see in a structure that cannot be fully taken outside and tested. The exterior has another problem. With no atmosphere to slow anything down, tiny rock and metal fragments hit the surface at tens of kilometers per second, faster than a rifle bullet by 10 times or more. Most micrometeoroids are sand grain sized or smaller. A good wall stops them. Several meters of regolith stops them reliably, which is another reason to bury the structure. But each impact that reaches an exposed surface chips it, pits it, or stresses it. Over years, millions of small hits carve micro craters across every exposed surface. Each crater is a stress concentrator, a place a future crack might begin. And occasionally a larger fragment arrives that threatens something more serious. Two strategies address this. The first is burial. Deep regolith cover absorbs impacts before they reach the shell. But burial was already in tension with heat rejection, the problem covered in the last challenge. Regolith insulates. It traps waste heat that needs to escape through radiating panels. That conflict does not disappear because micrometeoroids are also a concern. The second strategy is multi-layer outer skin design, where the outermost layers absorb an impact, intermediate layers arrest any puncture, and the innermost layer holds pressure while alerting the crew that a section has been compromised. Experimental materials push further, layers that melt and reseal around a small hole, foams that expand into a forming crack. Self-healing structures are a real research area with some promising lab results, but using them at whole base scale, in hard vacuum, under constant pressure, with hundreds of degrees swings and abrasive dust grinding for years, is mostly uncharted. No outer shell makes the risk zero. A large enough hit can still cause rapid decompression in a main module. When it does, hatches close, masks go on, the crew stabilizes pressure and locates the breach. And then, someone has to go outside and fix it. That is where the suit limit enters. All exterior repair on the moon happens inside a spacesuit, no exceptions. A suit weighs well over 100 kilograms on Earth. On the moon, it feels like 16 to 18, but the mass and inertia are still there. The pressurized gloves that protect the hands also fight every finger movement. Fine work, changing a small seal, tightening an awkward bolt, tracing a hairline crack along a curved surface, is far harder and slower than the same job done barehanded. What takes an hour on Earth can take a full working day in a suit, if it can be done in a single outing at all. And every suit outing burns consumables at a fixed rate. Oxygen, carbon dioxide scrubber capacity, cooling water cycling through the suit's thermal system, battery charge powering all of it. When those consumables approach their limits, the repair ends, finished or not. The window for each spacewalk is hard. The job must fit inside it, or the crew plans a second outing, burns another set of consumables, and adds another cycle of risk and effort. Look at what came back with them. Every suited worker returning from outside brings the lunar surface inside with them, at least partially. The suit is coated. A fine grey powder clings to the fabric, the joints, the boot treads, the gloves. It does not brush off easily. It does not fall cleanly to the floor the way earth grime does. It clings, because lunar dust is not ordinary dirt. Lunar soil has a name: regolith. It is rock that has been crushed by billions of years of micrometeoroid impacts, ground down particle by particle across geological time, with no air and no water to smooth what the grinding produced. On Earth, minerals that get broken up also get tumbled. Rivers carry fragments over rock. Wind moves grains against each other. Over time, edges round off. Particles become smooth. Lunar regolith has never had any of that. Every grain retains the edge it was born with. Under a microscope, lunar dust looks like broken glass. The Apollo crews noticed this immediately. Dust clung to their suits and tools by static charge. When they brought it into the lunar module, it scratched helmet visors. It jammed the joints of equipment. Mixed with cabin air, it had a sharp, acrid smell that astronauts described as burnt gunpowder. This was after a few days of surface operations. A permanent base would face this environment not for days, but for years. With crews cycling in and out constantly, equipment running continuously, and operations growing more intensive over time. Here is where the scale of the problem opens up. Lunar dust particles are typically in the range of tens of micrometers across, roughly the size of fine smoke particles on Earth, but with edges that look nothing like smoke. In a sealed environment, particles that size reach the deepest parts of the lungs. Big sand grains that you might inhale at a beach settle in the nose and upper airways and get cleared relatively quickly. Fine angular particles do not. They travel past the body's upper defenses and reach the tiny air sacs deep in the lungs where gas exchange happens, where oxygen moves into the bloodstream and carbon dioxide moves out. There they lodge, they irritate, they damage tissue. On Earth, workers exposed for years to fine silica dust from mining or cutting stone can develop silicosis, lung tissue scars, breathing becomes impaired, infection risk rises. The condition is chronic and progressive. Lunar dust is not identical to industrial silica, but it raises the same fears, and possibly more. Some researchers think regolith grains, sitting for millennia in vacuum under radiation, carry chemically active surfaces that could react more aggressively with tissue than ordinary mineral dust. The data is incomplete, but the direction of concern is clear. A base crew will live with this material surrounding them. People will go outside, work, come back. Suits will carry dust to the airlock. The airlock is where contamination must stop, and stopping it completely is an engineering problem that no simple door solves. An airlock cannot just be a door with a seal, not for years of operations. A real lunar airlock has to work more like an industrial cleanroom. One approach keeps the outer layer of the suits permanently outside, with crew climbing in and out from a clean interior side, so the contaminated exterior never enters. Others use vacuum systems, brushes, gas jets, or vibration to knock dust off before the inner door opens. Inside, multi-stage filtration traps fine particles, but filters clog and must be replaced. And dust levels throughout the habitat need continuous monitoring, because contamination builds in ways that are not always visible. But the lungs are only part of the problem. The machines face it too. Think about what tens of micrometer sharp-edged particles do when they get into a bearing, or a hinge, or a seal. They act like microscopic sandpaper, grinding away at coatings, cutting into lubricants, opening tiny leak paths through gaskets. Equipment that might function reliably for years in a clean environment wears significantly faster when abrasive particles work their way into every moving interface. Filters in fans and pumps fill faster. Pumps working against increasing resistance draw more power and wear faster. Seals that should last for years start to show deterioration within months. And then, the dust reaches the power systems. Solar panels on the moon enjoy one real advantage over Earth. No clouds, no atmosphere, no weather reducing the light. Sunlight arrives clean and direct during the 14-day day, but dust settles on every horizontal surface, and solar panels are exactly that. A thin coating reduces the light reaching the cells, and even a few percent loss matters on a system at its design limits. This is not theoretical. On Mars, dust on panels has reduced output enough to end rover missions. Mars has global storms to drive that. The Moon has no global storms, but it has something else. Every surface operation kicks up local dust clouds. Rover drives raise it. Rockets landing and taking off blast it. Construction work disturbs it. In a vacuum, particles follow ballistic paths rather than drifting in air, and some become electrically charged by friction or by sunlight, clinging to whatever they land on or briefly hovering above surfaces. There is no wind to carry dust away and no rain to wash surfaces clean. What settles, stays. Radiators face the same problem. Radiators work by emitting heat as infrared radiation into the cold sky, and how efficiently they do that depends on the properties of their surface. A thin coating of dust changes those properties. It acts like a thermal blanket, reducing the rate at which heat escapes. A less efficient radiator means the cooling system must work harder, or operate at higher temperatures, or be built physically larger. High operating temperatures shorten the life of electronics. A larger radiator requires more mass. Each path leads back to constraints already pressing against the base from other directions. And then, there is the question of what happens when the base starts to grow. The longer-term vision for a lunar base involves using local resources, mining regolith for raw materials, extracting oxygen locked in the minerals, processing metals, printing structural components. Every one of these operations intensifies the dust problem. Excavators scoop and dump regolith. Conveyors carry it. Crushers break it down further. Reactors heat it to high temperatures to drive off oxygen. Each step in that chain produces more fine particles, raises more clouds, introduces more contamination into the environment around the base. In vacuum, the mechanisms that manage dust on Earth do not apply. Earth's air carries dust in predictable patterns that ventilation can handle. On the Moon, particles follow ballistic paths with no drag to slow them, and electrical charging makes them cling to whatever they touch. Motors and joints in mining machines are directly exposed. Lubricants for vacuum must be chosen carefully, since standard ones evaporate or turn rigid, and even the best vacuum-rated lubricants face abrasion from grains that are, by terrestrial standards, exceptionally sharp. On Earth, heavy mining and construction equipment already needs intensive maintenance. Grit chews through seals and bearings, filters and cutting heads wear out. The industry built whole support systems around this. Workshops, spare parts inventories, specialist technicians, replacement machines. A lunar operation has a small crew, limited spares that arrived at enormous cost, and no supply run for months. The grains are sharper than anything on Earth. The free cleaning that rain and wind provide is absent. The repair resources are a fraction of what an equivalent Earth operation would need. The dust problem is external. It attacks surfaces, clogs filters, grinds mechanisms. You can see it settling. You can measure it on a panel or a bearing. You can, in principle, build a wall between it and the interior of the base and fight it at that boundary. The next problem has no boundary to fight at. It is already inside. It is the crew. Lunar gravity is 1.62 meters per second squared. Earth gravity is 9.81. That fraction, about 1/6, sounds manageable. A 90 kilogram person, roughly 200 pounds on Earth, weighs about 15 kilograms on the Moon, about 33 pounds. Heavy things become easy to move. Physical labor feels lighter. The environment seems forgiving in a way that radiation and dust and vacuum are not. But here is where it gets strange. The human body was not built to feel light. It was built for the full weight of Earth. And a gravity environment that removes 5/6 of that weight does not simply make life easier. It may quietly and permanently dismantle the body that depends on it. We have real data on zero gravity. ISS astronauts lose muscle mass and bone density. Their hearts change shape and workload. Fluids shift upward toward the head, since gravity no longer pulls them down. Faces puff, legs thin, headaches arrive, and pressure toward the eyes has been linked to measurable vision changes. These are not subtle effects. Astronauts exercise for hours every day specifically to slow the damage, and still need months of rehabilitation back on Earth. Now, consider what the lunar surface actually offers. Not zero gravity, not Earth gravity. Something in between. Something that has never been studied in humans over years. Not months, years. That is the gap. The ISS data tells us what happens at 0G. Earth tells us what happens at 1G. The Moon sits at 0.16G, and we have no long-term human data for that point on the scale. Sending a crew to a permanent lunar base does not enter a well-mapped regime. It enters a blank space on the map and begins generating data with the crew's own bodies, data that cannot be ungenerated. Start with the bones. On the ISS, without aggressive daily countermeasures, astronauts can lose 1 to 2% of bone mineral density a month, and not uniformly. It hits hardest on weight-bearing bones, the spine, hips, and legs. Some of that loss is recoverable, some is not. Even when density returns after long rehabilitation on Earth, the internal architecture can be changed. Healthy bone looks like dense support beams. Bone that lost mineral looks more like hollow lattice. The strength is not fully restored even when the mass comes back. The critical question is whether 1/6 gravity provides enough mechanical load to keep bone loss from starting. The skeleton responds to how much force it carries. Strong enough signals, and it holds its density. Too weak, and the body reabsorbs mineral as surplus. Whether 0.16G clears that threshold is genuinely unknown. If it does not, then treadmills, harnesses, and resistive machines may slow the loss, but not stop it. The crew could spend years losing bone mineral more slowly than in microgravity, but still losing it, with no way to recover while they remain on the surface. A population with progressively thinning bones, after 5 years, after 10, is a population where a stumble or a fall that would mean nothing on Earth means a fracture on the Moon. Older adults are especially vulnerable. The trap is that once a group has weakened skeletons, you cannot simply fly them home to rebuild. Much of the damage may be permanent, and flying them home has its own implications, which come shortly. The bones are only the most visible part. Fluids shift in microgravity because gravity is not pulling them down. At 1/6 G, the effect is probably reduced, but probably is not a data point. Whether it is 10% of the microgravity level or 70% is unknown. What we know is that chronic fluid pressure toward the head, even reduced, sustained over years, may affect vision, may raise intracranial pressure, may alter the environment the brain sits in. In microgravity, these effects are serious enough that agencies still study them and have not resolved the countermeasures. The Moon does not move them to zero. It moves them to an unknown point. The cardiovascular system adds another layer. The heart and vessels are tuned for 1G, regulating blood pressure across the constant posture changes of life on Earth. In low gravity, those adjustments are smaller. Over time, the system may tune down to the reduced demand, and the heart muscle may weaken if it no longer pumps against full gravity. Heart shape changes over years of microgravity exposure, and the cardiac risk implications, arrhythmia, heart failure, are still being studied. The brain, in a different pressure and fluid environment, may face changes that only become visible years into the mission. But even all of that, the bones, the fluids, the heart, is manageable in the sense that it involves adults who chose to go, who understood the risks, and who can in principle return to Earth before the damage becomes irreversible. The deepest unknown is not about the crew that arrives. It is about the children who might be born there. Think about what development actually requires. Bones, muscles, and organs do not simply follow a genetic blueprint. They respond to the mechanical environment they grow up in. A baby on Earth spends months learning to hold its head up, then to sit, then to stand, then to walk. Every one of those stages is a response to 1G pulling the body down and the muscles and skeleton adapting to resist that pull. The heart grows up pumping against the full weight of blood. The inner ear, the balance system, calibrates itself to a world where down is exactly 1G of pull. At 1/6 G, every one of those signals is different. A baby might sit up with almost no muscular effort, because there is very little to resist. Bones get weaker signals about the load they need to carry. Muscles may develop different fiber proportions. The inner ear may tune to a world where down is gentle, where falling feels slow, where standing costs almost nothing. By the time that child is a teenager, they may be fundamentally adapted to lunar gravity. Not because something went wrong, because the body did exactly what bodies do, which is adapt to the environment they actually live in. Then ask the hard question: could they ever safely visit Earth? Going from 0.16 G to 1 G multiplies the gravitational stress on bones, joints, heart, and circulation by roughly 6. A skeleton calibrated for 1/6 G may not be strong enough to carry a full gravity body. The heart may not be prepared for the additional pumping demand. The spine may compress in ways it was never built to resist. Earth, for a person raised on the moon, may not be physiologically accessible. Not difficult to visit, not uncomfortable, inaccessible. The way deep water is inaccessible to a body without the equipment to survive it. A moonborn generation that cannot return to Earth is not a research station anymore. It is a branch of humanity, separate not by distance, by biology, permanently tuned to a different gravity, permanently locked to the world where their bodies were built, permanently separated from the planet where their species originated. Even before that generation exists, the adults who go may reach a point of no return. Bone loss and cardiovascular reconditioning over 5 years, over 10, may mean that returning to Earth requires not weeks of rehabilitation, but years. Some may never fully recover the capacity to live at 1 G. A job assignment that began as temporary may become permanent not by choice, but by biology. The ethics of sending people under those conditions is not a simple calculation, and the biology of the crew is only one piece of what that small team must now manage. The base still needs power. It still needs materials. It still needs water. And the question of where the water comes from is, by itself, a problem that reaches into almost everything else. Behind every one of those breaths is a machine that just made it. On Earth, that fact never registers. The atmosphere handles the chemistry. Oceans, forests, and billions of years of biology built a life support system so vast and redundant that a single human exhaling barely moves the needle. There is always more air, always somewhere for the waste to go. The planet itself is the infrastructure, and it runs without a maintenance crew. On the moon, none of that background exists. Every molecule of breathable air inside a habitat is there because a machine made it recently. And every molecule of carbon dioxide from every breath has to be captured and processed by another machine. If either stops, the atmosphere drifts toward conditions that are first uncomfortable, then dangerous, then fatal. In a small sealed space with no removal running, CO2 rises fast. Headaches first, then confusion, then unconsciousness, then death. The timeline from normal to lethal is measured not in days, but in hours. And CO2 is only part of what the air system handles. People release water vapor, skin particles shed, plastics, electronics, and adhesives off gas, trace chemicals that on Earth simply disperse into the outdoor atmosphere. Inside a sealed habitat they accumulate, with no wind to dilute them and no window to open. CO2 scrubbers, oxygen generators, and trace contaminant filters must all run continuously, every hour of every day, for the entire mission. Not for weeks, for years. The International Space Station already does this. It has chemical scrubbers and oxygen generating systems aboard, and the crew breathes recycled air. So it might seem like a solved problem, something we already know how to do. But the ISS is not a closed loop. It leans heavily on Earth. When a scrubber cartridge runs out, a cargo vehicle brings new ones. When a pump fails, a replacement arrives within weeks. The ISS shows the technology working while the supply chain is still intact and fast. A moon base cannot count on that. Every filter, every canister, every replacement pump is mass that had to survive the rocket equation. Its systems must be far more closed loop, more reusable, and more repairable by whoever is standing there with whatever is on the shelf. That is not harder by a small margin. It is harder by a different standard. Water makes the constraint even harder. A person needs a few liters of drinking water a day. Add washing and cooking and it climbs into the tens of liters per person per day. For a small crew over years, the total is enormous, and shipping it all from Earth is not viable beyond a brief demonstration. Almost every drop must be captured and reused. Urine processed back into drinking water, humidity condensed from the air, grey water treated and cycled. The ISS already recycles about 90% of its water, a real achievement. But those systems are not light, simple, or maintenance-free. They need filter changes, pump servicing, and component swaps. And on the ISS, the ground ships replacements when something fails. On the Moon, if the main water recycler fails and there are no on-site spares, the crew starts counting days, literally counting how many remain in the tanks. And no fallback comes without its own complexity. Processing ice from permanently shadowed craters needs power, machinery, and its own maintenance chain. The stored tanks that form the emergency buffer are finite and limited, by the same mass penalty that governs everything else. There is no neighbor, no well to walk to. There is only what the machines produce right now from what they have. Food runs into the same wall. Short missions can carry freeze-dried rations. A crew of 3 for 6 months is a manageable supply problem. But a base operating over years, with more people, turns that into a continuous, expensive logistics chain that grows heavier with every additional crew member and every additional year of operation. At some point, the choice becomes binary. Either keep the base permanently tiny and rotating, or grow food locally. Growing food locally means large hydroponic or aeroponic farms, or something more ambitious. Full bioregenerative life support where plants, algae tanks, and possibly insect farming handle a significant fraction of the food supply, while also recycling CO2 back into oxygen and processing biological waste into nutrients. These systems can do real work, but they are not machines in the way a pump or a filter is a machine. They are ecosystems. And ecosystems crash. A fungus spreads through a crop. A nutrient imbalance stresses the plants before anyone notices. A lighting failure runs 4 hours during a critical growth phase. A temperature spike kills a batch. On Earth, a failed greenhouse is recoverable. Seeds, replacement soil, food from elsewhere while you rebuild. On the Moon, a major crop failure hits food security directly. And the only buffer is stored rations limited by mass and shelf life. There is no somewhere else. Tuning a bioregenerative system is slow, skilled work, requiring deep knowledge of plant biology and chemistry, in low gravity, under artificial light, with an unusual radiation background, in an atmosphere that may affect growth in ways never studied at scale. The rule running through air, water, and food is the same. There is no safe downtime. On Earth, an outage that knocks out HVAC is an inconvenience. Dangerous mainly for the vulnerable, rarely lethal for a healthy adult. On the Moon, losing environmental control for even a few hours can push conditions past lethal thresholds. CO2 scrubbing stops and levels climb. Fans stop and stale pockets form. Humidity control fails and condensation forms inside electronics. Cooling fails and the interior warms. Heating fails during the night and temperatures drift toward freezing, threatening pipes, tanks, and people alike. The obvious answer is a redundancy. Multiple scrubbers, pumps, fans, backup power, emergency oxygen. And redundancy is right, but every backup is more hardware launched through the rocket equation, more plumbing and wiring and sensors maintained by the same small crew. And it has a hidden failure mode. If 2 scrubbers share one software controller, a single bug takes both down. If 2 pumps came from the same flawed production run, they may fail together under the same conditions. Redundancy protects against independent failures, not common cause ones. And a base built with limited suppliers and little parts, diversity is especially exposed to those. There is no open window, no step outside for fresh air. Everything the crew breathes, drinks, and eats must be continuously manufactured, recovered, and maintained by systems that cannot afford to be merely mostly working, but continuously, reliably, repairable by a small team under pressure, 4 decades. That is a standard we struggle to meet in Earth's most safety-critical infrastructure, hospitals, submarines, power plants, with large dedicated teams and full supply chains behind them. On the moon, it is demanded of an entire artificial environment run by a handful of people who are also doing everything else. And all of it runs on power, delivered without interruption across the full lunar cycle. Power is not a background condition. It is the thing every other system quietly assumes. The scrubbers run on it. The water loops run on it. The grow lights, the pumps, the heaters, the communications array, the medical equipment, all of it. A base demanding continuous, uninterrupted power across the full span of the lunar cycle is not rhetoric. It is the load that sits underneath everything else. So let's ask where that power actually comes from. A modest science outpost draws tens of kilowatts just for life support. Add crop lighting, an excavator, a regolith processing oven, computers, a medical bay, and you reach hundreds of kilowatts. Scale to a real outpost with industrial activity, and you reach megawatt-class demand, roughly what a small town draws on a quiet afternoon. On Earth, that comes from a grid with redundant sources, continent-spanning transmission, and utilities with repair fleets and warehouses. On the Moon, it comes from whatever hardware the crew shipped, installed on uneven terrain, and now keeps running with their own hands. The first instinct is solar. It is a reasonable instinct. The lunar surface receives roughly 1,300 to 1,400 watts of sunlight per square meter, unfiltered by atmosphere, with no clouds to interrupt it. Panels run efficiently under those conditions. The sunlight is clean, direct, and reliable. For about half the lunar month, solar is genuinely excellent. That half of the lunar month is followed by the other half. The sun sets, and it stays set for approximately 350 hours. Not for a night, for 2 full weeks of unbroken darkness, during which the solar output drops to essentially zero. To survive that, the math becomes uncomfortable fast. A base drawing around 500 kilowatts on average through 350 hours of darkness needs somewhere in the range of 175 megawatt hours of stored energy, not 175 kilowatt hours, the kind of figure that describes a serious home battery, 175 megawatt hours. Battery fields or fuel cell systems capable of holding that energy would weigh many tens, potentially hundreds of tons, plus the inverters, control gear, and thermal management hardware those systems require just to function safely. And that is just the night storage problem. The solar array has its own difficulties. Panels degrade under lunar radiation as particles damage the cells. Micrometeoroids pit the surfaces. Dust from rovers, landings, and construction settles on the panels and cuts output, and cleaning is a trap. Brushing risks, scratching the glass. Gas blowing consumes resources. Automated systems are more machines that can fail. Because the array must supply base load and fill those huge storage banks during the day, the solar farm grows to cover multiple football fields of uneven terrain, wired through long cable runs that must survive dust, radiation, and the full thermal cycling. Every panel is more connectors. Every cable run can be cut, shorted, or degraded, and fixing a breakout in the field may require a spacewalk. The nuclear option solves the night problem cleanly. A compact reactor provides steady, round-the-clock output, ignoring the lunar cycle entirely, reducing the storage requirement to something far more manageable. The logic is compelling. But a reactor on the moon is its own bomb of complexity. First, it has to get there. Launching fissile material means convincing regulators and the public that a non-zero launch failure probability is acceptable. Rockets fail rarely, but rarely is not never, and a vehicle breaking apart carries different consequences when the payload is nuclear fuel. Second, the crew must assemble the reactor, shielding and cooling on the surface with no off-the-shelf infrastructure. On Earth, a plant plugs into an existing grid with a full regulatory framework, a professional workforce, and a spare parts supply chain. On the moon, the grid is whatever cables the crew laid, the spares are whatever fit the last manifest, and the regulations are still being written. Third, the reactor must run for years, dumping heat through radiators exposed to the same dust and micrometeoroids, that degrade every other surface. At end of life, there is no storage pool, no licensed repository, only a hot radioactive machine on the surface that must not contaminate the ice the water supply depends on. Not a solved problem, a permanent one. The likely architecture is a hybrid. Solar for flexibility during the day, nuclear for baseload through the night, large storage to bridge gaps and absorb transients when one source stumbles. On paper, the combination covers the requirements. In practice, a small crew is now running a power utility where every repair is hard, surface travel is slow, and the spare parts inventory is exactly what was shipped and nothing more. And there is no external grid to fall back on. On Earth, when a plant trips offline, others absorb the load. When a substation fails, dispatchers reroute. When a storm downs transmission lines, utility crews drive in from neighboring regions within hours. The system has depth, most of it invisible under normal conditions. On the Moon, the grid is the base. There is no adjacent region, no upstream utility. The system's full depth is the crew standing in front of it. Consider what a serious power event looks like. Dust has been accumulating on the solar panels for weeks, cutting output by a few percent at first, then more. At the same time, a coolant loop in the reactor develops a blockage, and the automated safety system does what it is designed to do. It scrams the reactor, shutting it down to prevent damage. The batteries begin discharging to cover the combined shortfall. Then a software error in the power management system overestimates the remaining battery capacity, and the discharge continues longer than it should. If everything goes right from this point, the crew diagnoses the coolant blockage, clears it, restarts the reactor, and brings the batteries back up before any system reaches a critical threshold. That is the good outcome. If anything goes wrong, it deepens. A valve needed for restart will not switch. An operator misreads a stuck sensor instead of actual coolant pressure. Module temperatures drift past the point where water processing must be suspended to protect hardware. CO2 scrubbers on reduced power near their limits. Within hours, the crew is evacuating outer sections, crowding into a smaller emergency core with better power and shielding, breathing from backup tanks, managing their own stress while planning a complex repair in a suit under a 14-hour cold soak. On Earth, outside crews bring parts and stabilize the system. On the Moon, the only technicians are already there. They are the people in the emergency shelter. They are the ones who now have to fix it. Because power connects to air, water, food, heating, and communication simultaneously, a serious power event does not threaten one system. It threatens all of them at once, through every dependency already documented in the sections above. What the base requires, held together, is power at the scale and reliability of a small terrestrial grid. Built entirely from equipment that arrived by rocket, operated by a crew the size of a small office, maintained without outside help for stretches that could span years. That is not an engineering subsystem. It is a civilization-level demand wearing the label of one, and power is still not the deepest layer. Beneath it sits the question of what raw materials the base is working with, and where all those tons of processed feedstock come from. Suppose the power holds, the grid is running, the reactors are stable, or the battery fields are charged, or some hybrid of both has threaded the needle through a lunar night. What then are the walls made of? Every serious plan for a lunar base eventually arrives at the same answer. You cannot keep importing the physical structure of the base from Earth. The launch cost alone makes that impossible. A single pressurized module, a room, a corridor, a storage tank, each one costs more to deliver than almost anything else humanity has ever moved. At some point, the base has to grow beyond what rockets can carry, and that means building from what is already there. The surface of the Moon is covered in regolith, tens of meters deep in most places. The raw material is everywhere. Melt it, press it, print it into bricks and beams and landing pads and radiation walls. Extract the oxygen locked inside the oxides. Pull out the aluminum and iron. On paper, the logic is clean. In practice, it opens a new layer of the problem entirely. Lunar regolith is not Earth construction material. That distinction sounds minor. It is not. Portland cement, the standard binder holding together almost every concrete structure on Earth, is made from limestone and clay processed with heat and water. The resulting chemistry is specific and well understood. Earth building codes, construction standards, material safety factors, all of them are built on top of centuries of working with that material. The Moon has none of the inputs waiting in usable form. No limestone quarry, no clay deposit, no accessible liquid water, no Portland cement, and no easy substitute. What regolith does contain is silicates and oxides of silicon, aluminum, iron, magnesium, calcium, and titanium. The elements are there, but in different proportions and mineral forms from anything the recipes engineers know depend on. Making something structural takes serious energy. Sintering, heating until grains fuse means hundreds of degrees Celsius. Fully melting and casting it means exceeding 1,000. Making glass, pulling out metals, producing ceramics, all sit in similar or higher ranges and require stable power, robust heaters, insulated crucibles, controlled molds, and carefully managed cooling. That is not a sideline operation. That is a full industrial process. Here the logic bends. The dream of Isuru using local material to build locally does not eliminate the industrial infrastructure problem. It moves it. Instead of steel mills and cement plants on Earth shipping components, you build mini versions of those facilities on the Moon. They run off the same fragile power grid, are maintained by the same small crew already running life support and thermal control, and consume feedstock that is sharp, abrasive, and chemically variable from one site to the next. The concept videos make it look simple: a robotic arm laying smooth layers of melted regolith, building a dome ring by ring, perfectly uniform and sealed. Real regolith is not uniform. Grain sizes range from powder finer than flour to small pebbles. Heat a batch and some grains fully melt, others only partially, others stay solid. The result is not a homogeneous material, but a mixture of fused and unfused particles, with internal voids, weak spots, and stress concentrations locked inside. Then comes cooling. Different minerals expand and contract by different amounts, so as the structure cools and its geometry locks in, those mismatched rates seed microfractures through the material. The fractures may be invisible and may not fail immediately, but they grow under repeated thermal cycling, and the Moon delivers that continuously. Every exterior structure faces swings measured in hundreds of degrees across each lunar month. Not a flaw in the design, a fundamental property of the material and the environment. To build reliably with regolith, you need more than a printer. Control of feedstock quality before heating, precise heating and cooling profiles, and inspection of finished parts for hidden flaws. On Earth, that means X-rays, ultrasound, destructive sampling, and safety factors built on decades of watching similar materials succeed and fail. On the Moon, you begin with almost none of it. There is no long database of how regolith-derived materials age under combined vacuum, radiation, micrometeoroid bombardment, and large thermal swings. Every printed arch, sintered block, and cast beam is closer to an experiment than a validated product. You will probably need binders and reinforcements on top of the base regolith, metals embedded as rebar, fiber woven through for tensile strength, polymers imported from Earth to hold layers together. Each edition introduces more logistics mass, more process complexity, more steps where something can go wrong in a facility that has no external technical support and very limited spare capacity. And then the problem scales upward again. Building the structures is one challenge. Maintaining the machines that build the structures is another. Truly reducing dependence on Earth means those machines have to support themselves. Gears wear, bearings fail, shafts break, casings crack, pipes develop leaks. Every mechanical component in the furnace, the printer, the excavator, the conveyor system has a finite service life. On Earth, you order replacements. On the Moon, you either made them locally or you are waiting for the next cargo window. Making them locally means machining tools, foundries to cast raw metal shapes, small metallurgical labs to refine the right alloys for the right applications. That is a second industrial layer sitting on top of the first. Push further and the ceiling appears. Truly independent manufacturing eventually requires fabricating electronics, and the computers and sensors running every other system are not simple mechanical parts. Semiconductor manufacturing is among the most complex activities civilization has ever created. Ultra-clean rooms, where a single dust particle ruins a component, dozens of chemical processes needing purities measured in parts per billion, lithography that writes patterns smaller than a wavelength of light, and a global supply chain feeding hundreds of specialized inputs from dozens of countries. Expecting a lunar outpost of a few dozen people to build anything approaching that from local resources is not ambitious. It is closer to asking a remote Antarctic research station to set up a full steel mill, an airplane factory, and a semiconductor fab using a few crates of starter equipment and whatever ice and rock are nearby. Even if the industrial problems are solved, the materials carry unknowns. Regolith glass may darken or grow brittle under radiation faster than models predict. Sintered blocks may crack slowly along hidden internal planes over years. Embedded metal reinforcement may corrode in unexpected ways when exposed to trace chemicals from life support exhaust recirculating through a closed environment. Structures optimized for 1/6 gravity may behave unexpectedly under internal pressurization or when carrying equipment heavier than planned. On Earth, building codes evolved from observation. Bridges stood or failed. Towers cracked or held. Engineers watched real structures age and updated their models, and the knowledge now embedded in construction standards represents centuries of trial and error, most of it paid for by structures that performed badly. The Moon has none of that record. Every dome, tunnel, and printed wall is among the first of its kind ever built in that environment, from those materials. No one knows with confidence how they will behave in year 5, year 10, or year 20. A miscalculation is not a crack in an unused building. It is a hairline failure propagating through a pressurized habitat roof, a slow weakening in a radiation shield that was rated for decades, a structural element that performed perfectly for 10 years and fails in year 11, in an environment where there is no margin for being wrong about material behavior over time. Izaru does not solve the problem. It trades one version of the problem for another. Instead of enormous launch costs for finished buildings, the base pays enormous complexity costs for a local industry that has no precedent, no safety database, no spare capacity for error, and no fallback when the materials it produces turn out to behave differently than expected. And all of it still depends on Earth for the high-end components the local industry cannot yet make. The supply chain does not go away. It changes shape. And the base, growing heavier and more complex with each section added, reaches further and further along that chain with every passing year. Start with what in situ resource use genuinely cannot supply. Regolith provides bulk, rock, some structural metal, eventually oxygen if the processing holds together. But a working habitat is not made of bulk. It is thousands of specialized items, each with its own supply story. Medicines with specific storage and expiry, processors and memory and sensors, specialty alloys for valve seats and pressure seals, pumps, bearings, inspection tools, instruments, cables, circuit boards, adhesives, replacement suits. None come from a regolith furnace, everyone comes from Earth, flown across 384,000 kilometers, landed and carried inside. And here the supply chain reveals its first quiet danger. It is not always the expensive item that matters most. $1 million pump can sit idle for want of a $5 gasket. A key environmental control unit can go offline because one small sensor failed. On Earth, a missing part is a phone call and an overnight delivery. On the Moon, if it was not on the most recent manifest, the crew waits. Not days, months. The system runs degraded or not at all, and the base absorbs the strain. That waiting time is not random, it is set by orbital mechanics. The geometry of when launches are cheapest repeats on a schedule the base cannot negotiate with. A part urgently needed in March may not realistically fly until a window opens in late summer. Every manifest is a negotiation between urgency, mass limits, cost, and the odds that any given item is the one that breaks next. Ship too many spares and costs balloon, while useful payload is wasted. Ship too few and a system sits grounded because one minor unique component broke with nothing to replace it. This is why launch cadence becomes a life support parameter, not a business detail, not a scheduling preference. A rhythm that human bodies and aging hardware depend on. People eat every day. Medicine expires on a calendar that does not care about orbital windows. Equipment wears at a rate set by the lunar environment, not by the resupply schedule. When a launch slips from June to October, the base does not pause. Its clock keeps running. But launches slip. Rockets are not buses on a fixed route. Engines and tanks wear. Pads erode and crack from repeated firings. Weather scrubs attempts. A major accident grounds an entire rocket family while investigators work, sometimes for a year. A recession cuts funding. A war disrupts component supply chains no planner anticipated. These are not theoretical risks. They are the normal background noise of complex industrial systems on Earth. The base on the Moon inherits all of it, filtered through a single thread. On Earth, that single thread is not how supply chains work. A container ship that fails to arrive triggers a reroute by air, rail, or truck. Insurance absorbs the shock. Multiple suppliers compete for the same contracts. Warehouses hold buffer stock measured in months. When one link fails, others pick up the load, because the network is engineered around the assumption that individual links will fail. Complex societies feel stable because of that depth. The buffer is invisible until it is needed, and then it is there. In cislunar space, that depth barely exists. If a cargo lander fails in transit, the food and medicine it carried are gone. There is no depot in lunar orbit holding reserves, no neighboring colony to borrow from. If an Earth manufacturer stops producing a critical component, there may be no second source qualified for space, and qualifying a new one takes years of testing and certification. Switching launch providers is not like booking a different airline. Payload interfaces and safety certifications are specific to each vehicle, and redoing that work takes time the base may not have. Something else was happening. The supply chain does not just affect what the base has, it affects how fast the base can fix what breaks. A design flaw found on Earth follows a fast loop. Engineers redesign within days, a prototype is machined and tested. The fix goes into production, and replacements ship within weeks. On the Moon, the same loop stretches almost beyond recognition. Redesign and testing now carry extra certification, because a failure on the Moon cannot be addressed quickly. Production is scheduled, parts are packaged into cargo modules and placed on a manifest, then wait for a launch window. After launch comes transit, orbit insertion, landing, and unloading. Only then can the crew install them. That loop runs many months, sometimes longer, not days or weeks, months. During that entire stretch, the base keeps running. It runs the flawed component more carefully, with additional monitoring and elevated risk, or it shuts down the affected system and pushes harder on backup systems, stressing them in turn. Every hardware improvement, every bug fix, every upgrade moves at the speed of orbital mechanics and launch schedules. Not overnight shipping, not a software patch. The speed of rockets and trajectories. That slowness reaches deeper than repair timelines. It shapes how the base treats change. In a harsh environment, you want fast iteration, trying something and adjusting when reality differs from the simulation. But each iteration on the Moon is long and expensive, and rolling back is slow and risky. So crews hesitate to experiment with critical systems because being wrong costs months of degraded operation. A conservative engineering culture develops, cautious and in some ways wise, but poorly suited to responding quickly when the environment exposes something no model predicted, which it does constantly. And the hardware that did arrive, sitting in radiation and dust and thermal cycling since the day it was installed, is quietly aging. It will fail. The question is not whether. The question is when, and whether the base has enough spares, enough tools, and enough skilled people to patch faster than the environment tears things apart. That hardware aging quietly is not a background detail. It is the central problem. Every system on the base has a rated service life. Every component came with a datasheet listing expected failure intervals and maintenance schedules. On paper, a lunar base is a set of systems with known lifetimes and predictable needs. In reality, it is hardware being worn down faster than those ratings predict, by an environment harsher than any laboratory that wrote the specs. Space ages materials in ways Earth never does. Electronics face constant radiation. High-energy particles flip memory bits, damage transistors, and slowly degrade the material. A control board rated for 10 years of service, tested in a climate-controlled building, does not live 10 years on the moon. Exposed to more radiation, violent thermal cycling, and the shock of launch and landing, that same board can quietly become a 3 to 5 year part, or less. The rating on the datasheet does not change. The board does. And electronics are only one aging mode. Lubricants outgas in vacuum, the oils and greases that keep bearings running evaporate, break down, or migrate away from the surfaces they protect. Polymers embrittle under radiation and temperature swings. Seals harden. Insulation cracks. Metals fatigue from thousands of expansion-contraction cycles. Solder joints flex until they crack. Connectors loosen. Cables stiffen and fracture from the inside out. Each is slow. Each is invisible until it is not. You can slow all of this with space-grade design, radiation-hardened chips, vacuum lubricants, robust thermal engineering. But every improvement costs more and usually weighs more, and there is a harder problem underneath. You cannot test for everything. Some failure modes only appear after years of real operation, under conditions only the moon produces. The engineers who wrote those datasheets did not run hardware on the moon for a decade and watch it die. They extrapolated. The moon will correct those extrapolations, one broken component at a time. On Earth, an early failure is a signal. The part is pulled, analyzed, and an improved version flows back into production within weeks, and the field population gets replaced before a cascade develops. On the moon, the same failure sends the same signal, but there is no warehouse to answer it. Only the small stock shipped with the base and whatever is on the next manifest, months away if funding and schedules cooperate. The mean time between failure rating, the number engineers use to predict when a part will fail, becomes closer to a rough guess for how long before the base starts running out of working units. This makes the spare parts problem staggering once you look at the mass. For any critical system, one unit is not enough. A water pump needs a primary, a backup, often a third, plus parts to rebuild the first two. A 20-kilogram pump becomes 40 or 60 before tools and test gear. Multiply that across every valve, motor, board, fan, filter, controller, and sensor. The lightweight habitat that looks efficient on a diagram is carrying an invisible twin of itself. Behind every active rack sits a shadow rack of backups. The mass launched is not just the base. It is the base, and the base again, compressed into storage. There is a partial answer. Standardize. One pump model across all systems. Shared spares. Modular swaps. It is genuinely more efficient, but it cuts both ways. A single design flaw or one bad manufacturing batch can then hit every system at once. The efficiency of shared spares and the risk of shared vulnerability are the same feature. And more spares mean more storage volume, more inventory to track, and more mass paid at every step of the rocket equation, reaching back to the launch pad. The crew carrying all of this is small, maybe a few dozen in the early decades. Yet that base needs electricians for power distribution, plumbers for water and cooling, technicians for heating and air, mechanics for equipment, software engineers for control systems, biologists for the greenhouse, and doctors and nurses for the inevitable medical problems, plus people trained in surface operations. These are not optional roles. They are the trades that keep a small industrial plant running on Earth. The base compresses all of them into a crew counted in dozens. Cross-training helps, expanding the coverage a small team can provide, but there is a ceiling. One person cannot be a master electrician, a skilled surgeon, a radiation health expert, and a reactor engineer, and also spend 6 hours a day on suited maintenance. The hours are not there. The cognitive depth is not there. Every repair competes for the same small pool of people. And if the one person who truly understands a system is sick, exhausted, or handling another emergency, the broken equipment waits. On Earth, an outside team flies in. On the Moon, there is no outside, no additional labor pool at any price. And some systems are too complex and dangerous for someone who learned them from a manual. A half-trained person attempting an unfamiliar repair on a reactor or a pressurized line is not a solution, but a different kind of risk. The software controlling all of these systems carries its own version of the problem. Life support, power, thermal control, radiation monitoring, and industrial processes do not run on manual commands. They run on automation, sensors feeding controllers that open valves, adjust pump speeds, switch power sources, and respond to alarms. This software is never finished. Bugs are found, features are needed, patches are rolled out. That is true of every software system ever built, and it will be true of the software keeping a lunar base alive. On Earth, a bad update to critical infrastructure is serious, but there are backups and clear rollback paths. Technicians physically reach the hardware and restore a working version within hours. On the Moon, that is not available. The one-way signal delay is only about 1.3 seconds, small enough to sound manageable. The problem is limited bandwidth, and that live systems cannot afford prolonged downtime while a patch is verified. Testing an update on Earth and in simulators before applying it to live systems is the standard of care, but the margin to do it safely is thin. The failure modes are not theoretical. A life support bug could misread CO2 and delay scrubbing. A power management bug could miscalculate battery charge during the night and trigger a cutoff when the batteries are not empty. A coolant bug could close valves in the wrong order and overheat hardware that is working perfectly. The equipment can be fine. Bad commands make it behave as if it is not. Rolling back is not a simple undo. Data compatibility must be checked. Configuration files preserved, jointly updated subsystems reversed together. Doing that carefully while your only systems administrator is also running medical checks and watching a greenhouse alarm because there are perhaps 20 people total and everyone carries multiple jobs, is a position no engineering team wants. Taken together, this is not a set of separate problems, but a stack. Faster hardware aging collapses service life estimates. Limited spares mean each failure depletes a reserve that cannot be quickly refilled. An overstretched crew means every repair competes with every other task. Software that must be nearly perfect runs on hardware being degraded by radiation, where updates are hard and rollbacks costly. You're asking a small group to hold a complex, interdependent machine at the edge of failure, year after year, with almost no outside help and a supply of parts and expertise that can only diminish faster than it is replenished. Reliability on the Moon is not a specification to be met. It is a timer. And while they manage all of this, the environment is also working on their bodies. Behind every one of those repairs is a person who is also tired, who is also missing something, who has not touched grass or breathed outdoor air or stood in a room larger than a corridor in months, possibly years. The machinery is the problem we have spent the last several sections building. But the machinery runs on people, and the people are running on something that the Moon is quietly draining as well. Start with the simplest version. Take 30 to 100 people. Seal them inside a metal and regolith structure with no way to physically leave. Tell them to live together, work together, and depend on each other for years. Then add chronic stress, demanding technical work, constant low-level danger, shift schedules, cycling through artificial light, and the unrelenting hum of machinery in every wall. That is the social environment of a lunar base. Not a description of it, but the actual daily texture of living inside it. People have done versions of this. Antarctic stations run for months sealed in by weather and darkness. Submarines confine crews for weeks. Both are small and monotonous, and both produce, even with careful selection and professional psychological support, the same catalogue of outcomes: personality clashes, leadership disputes, relationship breakdowns, mental health struggles. The research is not ambiguous. Isolation and confinement do this to human beings, predictably, even when they are experienced, screened, and motivated. The answer was stranger than expected. Every one of those Earth environments sits inside a breathable atmosphere. A conflict on a submarine ends when the captain sends someone home at patrol's end. An Antarctic mental health crisis can, in a serious case, trigger an emergency evacuation. The exit exists. It may be difficult, it may be expensive, but it is there. On the moon, there is no exit, slow or quick, in any practical sense. Every return seat is a scheduled event planned months or years ahead, dependent on spacecraft readiness, orbital alignment, and launch windows the base cannot negotiate with. If someone becomes unstable, aggressive, or slides into a depression severe enough to compromise their function, the options are limited to whatever the base can manage internally. You cannot put them on the next plane out. There is no next plane. This turns what would normally be a personnel problem into something harder. A serious feud between two key engineers, a collapse of trust in the commander, a faction forming around competing priorities. These are not just uncomfortable social situations. They are mission-level safety risks, because the people who stop cooperating are the same ones who share life support duty, surface walk watch, and reactor monitoring. A breakdown in trust does not stay in the human resources domain. It bleeds directly into operational safety. There is also almost no privacy. Habitats are compact because every cubic meter of pressurized volume costs mass. Sound travels through the metal. Air is shared. You hear co-workers sleeping. You share bathrooms, gyms, labs, sometimes bunks. Relationships form in that small bubble, some stabilizing the group, others fracturing it. Informal power networks and cliques develop. Small grievances grow large because there is nowhere to decompress, no outside world to step into for an hour and return calmer. The bubble is total. Now layer on top of that the medical reality. On Earth, when something goes seriously wrong with a body, the response is fast. Emergency services reach a stroke patient within minutes in most cities. Helicopters land on hospital rooftops. Specialists are called in. Even in genuinely remote regions of the planet, a critical patient can usually reach a major hospital within a day. The moon has none of that. The medical facility is whatever the base was funded to include. A small infirmary, maybe an operating room if someone prioritized the mass, some imaging, a limited pharmacy. The doctors are whoever was sent, likely one or two broadly trained physicians and crew with first aid cross-training. For a sudden cardiac event, a traumatic surface injury, or a fast-moving infection, only the people already present can help immediately. Earth can offer advice across a 1.3-second delay, but it cannot send equipment or a specialist, and physical presence is the thing that saves lives in emergencies. Evacuation is not a backup plan that simply takes longer. It requires the patient to be stable enough to survive a launch, days of cramped transit and re-entry, plus a ready spacecraft, favorable orbital mechanics, and enough life support capacity in the return vehicle. Many emergencies survivable on Earth given fast intervention will not be survivable on the moon, not because the technology fails, but because the geometry makes fast intervention impossible. The crew knows this, and the awareness changes behavior in ways hard to predict. Some become overly cautious, slowing on risky tasks, second-guessing fast decisions, accumulating a kind of psychological debt from the constant calculation of what happens if this goes wrong right now. Others go the opposite way, numb to the risk or fatalistic about it, which carries its own danger when it shows up in someone responsible for a pressurized system or a reactor control. And the link to Earth, while functional, is not emotionally equivalent to being close. The 1.3-second one-way delay is small, video calls, and remote support work. But real-time conversation feels slightly off, the lag enough to make back and forth unnatural. And the cadence of physical contact is not weeks or months, but yearly, possibly less, depending on launch availability. Friends and family become voices on a screen, letters, and recordings. The crew is not just geographically distant from Earth, they are temporally out of sync with it. Festivals pass without them. Elections happen while they watch on a delay. Cultural shifts, crises, and trends move through civilization and reach the base as news from somewhere they no longer quite inhabit. A frontier crew can start to feel like they live in a side story, cut off from the main current of human life. Faster communication does not fix that. It is built into the low cadence of physical presence and the radical separation of lived experience. It is the structure of the situation. And then consider what happens when the base becomes permanent. When the first children are born there. We traced the biology earlier. A child raised at 1/6 gravity develops differently, bones and muscles and the cardiovascular system responding to the signals they actually receive rather than the ones Earth evolution assumes. Those children grow up with grey dust underfoot and a black sky overhead. Their social circle is the base population. Earth is the place their parents talk about, a blue sphere they may never safely visit because their bodies were built by a different gravity. Their reference for normal is not Earth's. Their priorities will not be Earth's. And over time, those priorities will diverge from the agencies, governments, and corporations funding the base, setting the schedules, and writing the rules. A generation raised on the moon will push back against quotas and work structures designed by people who never lived a day in 1/6 gravity. They will want different things and hold different values. This is not specific to the moon. It is how communities behave wherever a frontier develops a generation too young to remember the center. The difference is that this edge cannot easily supply itself. It cannot revolt and leave. It is physically locked to Earth's logistics and technology in ways historical frontiers never were. The first American colonists could grow food and build shelter from local materials. A lunar community cannot fabricate its own processors, synthesize its own medications, or build its own spacecraft. The dependence is structural and probably permanent for a long time. So what develops is not independence, it is friction, deep and lasting, between a population whose home is the moon and a civilization whose money and technology make that home possible. What you are left with is a base where everyone knows they depend on fragile machines, where fast rescue is impossible, where the same faces appear every morning for years in a space the size of a few connected corridors, where one major failure can kill not just individuals, but the entire community at once, where the children born there may never leave, where even solving every technical problem on the list leaves this question completely open. How long can a small group of human beings live under that pressure without serious breakdowns? We do not have a good answer. The analogs we have are short, and none of them were permanent. And while psychology and community dynamics remain an open question, there is another layer the crew cannot control at all. The laws, the politics, and the power struggles happening back on Earth. And while they live with all of that, the rules under their feet are still being argued about. 250,000 miles away, the physical ground may be unstable, the legal ground is almost worse. Modern space law grew out of the 1960s and 1970s, written in a world where spaceflight meant short missions, planted flags, and the collection of rock samples. The Outer Space Treaty, still the foundational document governing human activity beyond Earth, was designed for a specific image of space exploration. Astronauts arrive, astronauts leave, no one stays. The reading came back reversed. The treaty says no nation can claim sovereignty over the moon. No country can legally declare a crater its territory. That sounds like a sensible, peaceful foundation. It sounds like a guarantee against conflict. It is not. It leaves enormous gaps. If you cannot own land in the usual sense, what exactly is a base? Who controls the ground beneath it, the roads to it, the landing pads beside it, the rocks pulled from it? Can a company declare a surrounding area off limits as critical to safe operations without ever claiming ownership? The treaty says no sovereignty. It says almost nothing about operational control, buffer zones, or the space immediately around an active industrial site. So a base under those rules can still land at the center of a dispute about everything except the one thing the treaty addressed: Resource rights are even less settled. Some readings of newer agreements and national laws say you can own what you extract without owning the land, the water pulled from the ice, the metals refined from regolith, the oxygen electrolyzed from the soil belong to whoever processed them. Others dispute that entirely. The United States, Luxembourg, and several other nations have passed domestic laws letting their companies mine and own space resources. Not every country agrees those laws are valid under international frameworks, and not every agency reads them the same way. So a real base operates in a grey legal zone from day one. Multiple nations, multiple agencies, multiple corporations, all claiming to follow the rules, all strongly disagreeing on what the rules actually mean. That legal fuzziness might be manageable if the resources were spread evenly across the surface. They are not. Water, the resource a base needs most, is clustered. Lunar polar ice does not spread across open plains. It sits in specific craters and permanently shadowed regions, cold traps that have stayed dark for billions of years, cold enough to preserve volatiles that would otherwise evaporate. The total accessible ice is probably limited, and the richest, most reachable deposits are concentrated in a small number of locations near the poles. Water is not just drinking water. It is breathable oxygen, split from the molecule. It is hydrogen and oxygen for rocket fuel. It is the life support buffer that keeps a base alive when recycling systems underperform. Whoever controls a rich ice deposit controls something that everyone needs. If one country or company sets up at a major ice deposit and extracts aggressively, others will argue access must be shared. But you cannot run unlimited heavy industry inside a narrow, shadowed crater without interference and real safety risks. Machines collide. Dust and debris contaminate neighboring equipment. The logistics limit how many operations can share a small space, regardless of what agreements say. Control of a small area becomes outsized influence over everyone who depends on that resource. On Earth, choke points have always worked this way. Sea straits, canal passages, mountain passes. Control a narrow geography and you hold leverage over everything moving through it. An ice-rich South Pole crater could play exactly that role, with far fewer established rules, far less institutional enforcement, and far more uncertainty about what would happen if a dispute became serious. That is the resource question. But it does not sit alone. Even a base with entirely peaceful goals does not exist in a strategic vacuum. The hardware that runs a large, capable, independent base carries obvious dual-use potential. High-bandwidth arrays that relay base operations can relay other signals. High-resolution sensors that track approaching cargo ships can track other things. Precise navigation beacons that guide landers can support spacecraft maneuvering more broadly. Reactors powering life support could, in principle, support energy-intensive applications no one publicly describes. From a rival's perspective, a base equipped with advanced sensors, strong communications, precision landing infrastructure, and nuclear power does not look like a research station. It looks like a high-ground installation, a fixed platform outside the atmosphere, above the interference of weather and air, with a clear line of sight to much of space and parts of Earth. No weapons required. The potential is there regardless. And as more actors join, trust does not improve. Each new country, alliance, and corporation entering cislunar space is one more participant wondering whether the others are genuinely doing science and mining, or quietly building strategic advantage. That uncertainty does not stay in diplomatic conversations. It spills into funding decisions and into willingness to share navigation data, rescue protocols, and emergency communications. Cooperation that would make a base cheaper and safer, to run fractures under the weight of suspicion no one can fully disprove. Wait, the hardware required to keep people alive, and the hardware required to project strategic presence are, in many cases, the same hardware. There is no clean line between a peaceful capability and a strategic one. Then there is the question of what happens when something goes wrong. A resupply launch fails on ascent and drops debris onto another country's territory, or releases toxic propellant. Who pays? Launch liability agreements exist, but they were written for occasional missions, not constant heavy cislunar traffic. A reactor leaks and contaminates an ice-bearing crater that 3 different bases depend on for water. Is the operator liable? The sponsoring nation? Under which law, in which court, for an event on the moon, caused by hardware run by a private company under a national license, damaging infrastructure owned by an international consortium? These questions do not have clear answers. They have competing answers, each defended by lawyers working for different clients. The scenarios that keep insurers and investors nervous multiply quickly. A cargo lander crashes and damages another nation's base. A navigation error causes a near miss between two cargo ships in lunar orbit. An industrial accident throws a cloud of excavated dust across a neighboring solar farm. Each case mixes space law, international law, national law, and private contracts in ways that have never been tested in any real jurisdiction. Not vague disagreement, no legal resolution at all. Sorting out fault later is a weak pitch when you are asking investors or taxpayers to commit tens or hundreds of billions of dollars. Unclear liability means unclear risk, and unclear risk means higher costs. Companies price in the exposure. Governments argue over who is responsible if a partner defaults. And no one can calculate what a bad outcome costs until after it happens. This is another layer of instability, sitting above all the physical, biological, and operational risks already stacked underneath. The people inside the base depend on machines that may fail, on their own resilience under pressure no analog has fully captured, on treaties written before anyone imagined this situation, on promises from governments that change with elections, and on funding that can be cut when priorities shift. A technically working base, solving every engineering problem on the list, still sits inside a web of incomplete law, strategic suspicion, and financial uncertainty it did not create and cannot resolve. That question reaches further than any crater, any treaty, any military calculation. Behind every legal argument and every budget negotiation sits something simpler and harder. Who actually pays for all of this? For how long? And why? The International Space Station cost on the order of $100 billion, accumulated over decades across the United States, Russia, Europe, Japan, and Canada. It supports a rotating crew of perhaps half a dozen, in low Earth orbit a few hundred kilometers up, where resupply is relatively straightforward and an emergency return takes hours. $100 billion, multiple nations, decades of work, and you get a small pressurized laboratory that cannot go anywhere and cannot survive without continuous deliveries from below. Now, scale to the moon. Distance jumps. Energy cost jumps. Every kilogram gets more expensive to place, harder to maintain, harder to recover if something goes wrong. A serious semi-self-sufficient base with multiple interconnected habitats, shielded quarters, an industrial ISRU operation, a medical bay, redundant power, landing pads, and spare parts for all of it, will almost certainly push past the ISS investment level. Not by a little, by a lot. Here the economics get uncomfortable. The ISS earned its budget partly by delivering a steady stream of microgravity research with clear near-term value, pharmaceutical, material science, fluid dynamics, biology. Institutions could point to results, papers, spin-offs. A lunar base in its early decades offers nothing equivalent. You are asking nations to pour in money equivalent to several large national infrastructure programs, then keep funding operations, repairs, and expansions across election cycles and recessions and crises. The profit, if it ever comes, is not a 10-year business plan. It may be a bet held across generations, outlasting everyone who made the original decision. But here's where it gets strange. Every time someone makes the economic case for human presence on the moon, there is a competitor in the room that is very difficult to argue with. Robots. Every scientific purpose used to justify humans has a robotic version. Study lunar geology with rovers carrying drills and sample return capsules. Want atmosphere-free telescope platforms, put instruments in orbit or at gravitational balance points. Map ice and minerals with orbiters and automated landers. Robots need no radiation shielding. They do not eat, sleep, get depressed, or need surgery or a ride home. A failed robotic mission is a budget line item. A failed human mission is something else. And you can often send 3 or 4 robotic missions for the price of one crewed one. Every serious budget meeting eventually arrives at the same question. Why not just send more robots? The humans in the room have to clear that bar. Not emotionally. Economically. Supporters of a lunar base point to markets that might change this calculus. Helium-3 mining for fusion power. Off-world manufacturing in low gravity for specialty materials like certain optical fibers or high-purity crystals. Lunar tourism. Space-cooled data centers. Each of these sounds plausible in outline. None of them exists at any scale relevant to justifying a base today. Helium-3 fusion is not a working power industry. There is no commercial reactor anywhere on Earth where you can point to a quantity of helium-3 and say how many cities it would power or what it would earn. The technology is still in research, and mining a resource, hoping its industry eventually materializes, is a gamble of extraordinary size. Off-world manufacturing of niche materials is promising, but current experiments are small-scale, aboard orbital stations, serving modest markets. Turning that into revenue able to sustain a multi-billion-dollar base is a large commercial leap with no proven landing point. And tourism runs into hard arithmetic. Each visitor rides an expensive, dangerous rocket, needs training, accepts minimal emergency care, and faces enormous insurance costs. The numbers stay low for a long time, nowhere near covering capital and operating costs. Most of the supposed lunar markets live on presentation slides, concept art, and speculative reports. They do not generate the steady, high-volume revenue a self-sustaining lunar city would actually need. You would be building the most expensive infrastructure project in human history on largely theoretical economic foundations. And there is the question of what else that money could do. Not nothing, but what else you could build for the same commitment. The same investment could go into climate adaptation, seawalls, redesigned agriculture, clean energy grids, work that protects hundreds of millions from risks already arriving, into global disease surveillance and vaccine capacity, into faster transport or better education, or into more practical space assets, next-generation Earth observation satellites, and expanded orbital networks that multiply the value of every other mission. Leaders do not ask only whether a moon base is possible. They ask whether it is the best use of this much money, and in that comparison, a base competes not against doing nothing, but against fixing coastal flooding and preventing the next pandemic. That is very hard to win on a 10 or 30-year horizon. Stack it all together and a pattern emerges. Nothing in physics forbids a permanent human presence on the moon. Rockets reach it. We know how to land. We understand shielding in principle. The ISS showed that closed-loop life support, water recycling, and solar power in space are achievable. Piece by piece, none of it is magic, but physics is only the foundation. On top of it sit the rocket equation's mass penalties, radiation that never turns off, 300-degree temperature swings, razor-sharp dust, unknown biology at 1/6 gravity, a fragile logistics chain, hardware that ages too fast, a small crew covering every trade, incomplete law, strategic suspicion, and generation-scale spending with weak near-term returns against urgent terrestrial needs. Together, they produce something physics permits, but almost everything else blocks. For our current civilization, it behaves like impossible, not because nature says no, but because how we live, spend, and argue says not yet. What would flip that? Not one breakthrough, but all of them, arriving together and holding. Launch costs dropping by another large factor and staying low at high cadence with real reliability for decades. Life support moving from a system that works on the ISS with constant resupply to one that runs for years on minimal spares and local repair, for far more people than any station supports. ISRU moving from lab demos to rugged industrial systems, chewing through regolith and ice, daily without grinding to a halt from dust and wear. Power systems, solar or nuclear, reaching a reliability that shames current grids with no field service team on call. Decades of stable international agreements, surviving elections, recessions, and crises so funding does not lurch with each government. Clear legal frameworks on mining rights, liability, and coexistence. And an economic story beyond the word inspiring. Maybe off-world manufacturing finds a killer application, maybe space-based solar power becomes viable, or maybe a coalition of nations commits to a second branch of human civilization as long-term insurance, the way past societies committed to cathedrals with no expectation of near-term profit. Right now, none of that exists at the required level. Some pieces are moving in the right direction. Launch costs are trending down. Robotics are improving. Interest in the moon has grown. But nothing is proven at the scale, the duration, and the tight integration a real base demands. The gaps are large enough that filling them with "we will figure it out as we go" means gambling with human lives. Think of a base not as a project, but as a civilizational phase change. The pyramids took generations of centralized authority and a large fraction of an economy. Gothic cathedrals took centuries, built by people who knew they would never see them finished. The internet took decades and trillions of dollars, layered technologies built by thousands of organizations with no single plan. A permanent crewed lunar base belongs in that company, not a 10-year mission, not one program or company or administration, but a commitment to build and maintain a second artificial human environment in one of the most hostile settings ever attempted, continuously, through all of Earth's upheavals, for longer than a generation. The real question is not whether we can get there and survive. It is whether we can keep this alive when the original designers have retired and the first children born on the moon have grown up. That is measured in civilizations, not election cycles. Calling a base impossible in this context is not drama. It is pushback against one small word. Just. Why don't we just build a lunar base? That word hides everything examined here. The exponential rocket equation, buried radiation shelters, megawatt power across endless day and night, dust-proof industrial machinery, unknown biology at 1/6 gravity, logistics threaded through orbital mechanics, unbroken political will across generations, and a business case that must beat fixing the problems already pressing at home. Physically, the door is open a crack. Civilizationally, we are still standing far away, arguing about whether to walk toward it. A human-crewed lunar base is not something we build today. It is something we study, simulate, prototype in pieces, and reach for. And whether we ever close that distance depends not on any single rocket or any single reactor or any single treaty, but on whether the civilization that sends people there turns out to be the kind that can also keep them there.